Okay, what do we have here? We have a good case of condensation. And why do we have that condensation, and what are we looking at? So let's back up and let's look at the big picture. Recognize those words? The big picture? So let's look at the big picture here. We have a dehumidifier, but we have a dehumidifier that was meant to be placed inside the location of which it's dehumidifying. And that is how this is designed, because it has so many air leaks on it. It doesn't matter if it leaks within the same room that is actually dehumidifying, because humidity and temperature and everything is all the same. So what is going here is it was asked to be placed outside of the room in which it is dehumidifying. Well, in this locality, it just got down to 32 degrees outside, and even within the warehouse it got down into like 39-40 degrees. So the area that it's dehumidifying is roughly 70-80% humidity at 81 degrees Fahrenheit. So you have this saturated, moisture laden air with tons of water in it, and as the air passes and comes into here, it contacts the outer surfaces. All over here is wet. All these outer surfaces, this plate, all this water here, this is all condensation. Look at the capacitor. The capacitor and all the wires and everything are just soaked with water. The controls were soaked with water. The controls were dripping with water. All because this is an indoor unit that has been mounted outdoors. And it's protected from the wind, it's protected from the rain, it's protected from the sun. So it's under a roof. There's the roof, but it's in a unconditioned warehouse that the inside of the warehouse basically becomes near the temperature of the outside. So in this situation, we had a massive amount of water accumulate. It poured out, it leaked through the roof downstairs, which I kind of knew what was going to happen. That's why I really told them these need to be mounted and put inside the room, but it couldn't. The next rooms are going to be designed different, so they can, and actually I might eliminate these, and I'm going to put a hydro reheat heat recovery kit with the LG system, where I take the third pipe waste gas that normally would be hot air, hot energy. The energy, the heat removed from the room from process, would go up to the roof on the condenser and be ejected as hot heat into the atmosphere. But what I'm going to do, since each one of these dehumidifiers are over $1,000 a piece, and they have 2 up here, and they almost need 3 up here, so just in the dehumidifier unit alone, just the unit, you're talking what happened to my math? $18,000 in dehumidifiers. Then you have the installation cost of another $3,000 a piece because of the ducting that has to be in this cage that has to be constructed to support it, the engineering to put this cage and everything like that. You got $3,000 a piece in labor. Then you have another $2,500 to $3,000 in materials to install the dehumidifiers. So with that same amount of money, oh, and not only that, to run these dehumidifiers, the energy you have to consume to run these dehumidifiers all the time, I can't remember, I'm pulling, I think, about 6,000 watts each dehumidifier to dehumidify every room. So now on top of that, you have energy consumed to dehumidify the air. You have extra labor that was never needed in the first place because they were placed out here. You have extra materials that were needed that were never needed if they were mounted in the room. Then you have the energy consumed to dehumidify the room, ×2 or ×3, depending on how many dehumidifiers are on in this one room. We're just talking this one room. There's going to be 3 more rooms identical built like this, all in a row. You got 20 tons of heat pump or heat recovery unit on the roof. So what I'm going to do is I'm going to grab that third pipe of heat, that is energy that the customer has paid PG&E to remove heat out of a room. The customer has paid PG&E 24/7 to run this dehumidifier nonstop from morning to night for the rest of its life. 5 years, 10 years, 15 years, whatever that is, at high energy rates. On top of that, the heat that is put off by a dehumidifier goes back into the room, and for every one of these of this size, you're adding 4 to 5 tons of cooling extra that is needed to cool off the air that is added to the room because you're using these dehumidifiers. So you have that extra energy cost, and you have to buy and purchase extra tonnage of air conditioning just because you're using one of these dehumidifiers. Now, I take that reheat gas and I run it into a plate heat exchanger to heat water. So now I have a large tank of nothing but water, just a simple tank, not expensive, not complicated, a simple insulated tank of hot water that gets heated by the waste gas from cooling the processing room to cool all the equipment, all the electrical components that need to be cooled in that room that normally would go to the atmosphere. It just gets rerouted into water, and now you have this large tank of hot water. So what will I do with that large tank of hot water? I'll eliminate these dehumidifiers. So all the money that was spent on the electrician to make home runs of each one of these dehumidifiers all the way back to the electrical panel, eliminated. All the extra energy to run each one of these dehumidifier in every room, and look, this one room needs 3 of these 500 or 700 pint dehumidifiers. It needs 3 of them. All that electricity to run 3 of them to make dry air, eliminated. All the extra electricity that is needed to add in tonnage of cooling to cool the room, because each one of these are putting 4 to 5 tons of heat into the room. You need that much more cooling to cool the waste heat from these off. So you take that hot water that you just made from the cooling of the room, and instead of wasting it to the air, you got hot water. Now you take that hot water, and here's the air coil, here's the air handler, here's your evaporator, depending on your terminology and what level you're at. Okay, this is where you make your cold air, right here. So we have a coil sitting right here, and the hot humid air is coming from, I have MERV 16 filters in there. You got clean filtered air, and it hits the coil. So it's 80 degrees at 80% humidity, and it's hitting this coil, and it's turning into water, and it's coming out the condensate, well, not this condensate drain, it's coming out the condensate drain and going down. Then you take that hot wire and you get water, and you put another coil right in front of the air hole. Right here, coming out here in this direction, is cold air. So now we have semi dehumidified air that is cold. And during normal daylight hour operations, when air conditioning is running, it naturally removes a certain quantity of water, and that would do great in the daytime and when you have all your electrical equipment operating. But as soon as you turn off all your electrical equipment with a night load, the air conditioning stops, and your dehumidification due to the air conditioning stops. You cannot run air conditioning in the night with no load on it. It would overcool the room, and it would just cease to work once it got down below a certain temperature, because the physics stop the dehumidification process with the limit of the equipment. So then what you do in the nighttime mode is you get that hot water, you put another coil here, and the air conditioning turns on and starts cooling air, turns to a low temperature, and it starts dehumidifying the air. Well, now you're in the night mode, and you have this cold, dry air, and then you run hot water through another condenser, another heat exchanger that you put in front of this cold air, and you warm it back up to the temperature you need for the room to keep it at. So if you wanted to keep the room at 70 degrees or 80 degrees at nighttime, you run the air conditioning, and you take that waste gas and you heat water, and for nearly free, other than some water piping and a small pump, you run it through a coil and you reheat your air. Now you have this system on several different rooms, and you have a processing plant that has 3 shifts running 24/7. So you always have some rooms on the system that are doing cooling, making waste hot energy, hot water. And so that would normally be thrown away, money from PG&E spent, thrown away to the atmosphere, but instead you shift it over to this room in the form of water that is heated, and just run it through a coil and you reheat. So you did not have to spend any extra money to heat water to reheat your air that you cooled using the air conditioning mode. And you completely eliminated every dehumidifier, all the labor involved, the electrician's labor involved, all the wiring and conduit for the electrician, all the mechanical support and everything that was needed for this gets eliminated. The ducting gets eliminated, the insulation gets eliminated, everything. All that is many times more expensive than it is to add a reheat system on a VFR. And that is going to be the end game on the other 3 rooms after finishing completely finishing this room. Once we get this all up with the set controls and everything like that, and the monitoring system and the remote monitoring operation, you could be sitting on the beach in Tahiti enjoying your cocktail, and you can monitor your room and change temperatures from the beach on your cell phone. That's how this whole system is getting set up. And I'll be putting a reheat as a guinea pig for the customers on this one to show them how the system works. And it'll be a kind of a temporary thing. It's going to be a guinea pig thing on this one, so I can actually show them, and we can figure out the calculations of how many pounds of water for their kind of process. Because even though these guys are in the same business as many other guys, everyone has their unique operating and manufacturing process that produces so many pounds of water per hour, and they're all drastically different. And so we're actually measuring right now every gallon of water that comes out of every one of these dehumidifiers. We're measuring the gallons for every hour it operates 24/7, so we know how many pounds of water needs to be removed. And then for every air handler, there's 6 air handlers in this room, a mixture of 8 ton and 6 tons. We're literally measuring every gallon of water that comes from the air handlers during normal daytime full load application, so we know exactly how many pounds of water has to be calculated to figure out the size of the reheat coil that we need, to calculate how many gallons of water need to go through that coil per hour, what the flow rate is, the size of the pump, the electrical consumption, and everything like that. It's all math. It's all really simple. And if you take direct measurements and you already have a prototype, this can all be figured out without making mistakes. That engineers always make mistakes because they're only as good as their information, and the information they're given out of calculations from books is not that great. So this is a process that we're going over by and showing you an example here of running a piece of equipment in a ambient condition that it was never meant to be ran in. So I'll fix this by insulating all the cabinets on the outside, so the temperature will never get cold enough to the condensate point and get like this, and that'll take care of all this leakage that's happening down here where it's turning to water and pouring off, which I kind of knew was going to happen. Told them shouldn't be put outside but they had to because of the size restriction. The room was not developed right, it wasn't sized right. It started before the managers who kind of came over and taken over in this project, and this was all determined before they contacted me, because if they would have contacted me, I would have them raise the roof of their room another 5 or 6 feet or more, which was easier and cheaper to do than all of this. Up here with all the extra ducting, you have another $50,000 in ducting, and then you have another $18,000 in labor to install the 3 dehumidifiers, and all that could have been avoided by adding say 5-6 feet to the roof height, which was much cheaper and faster. All right, gentlemen, I'll see you later. Oh yeah, by the way, this happens inside the ceiling and walls in wooden houses. If you've ever seen a house that had siding that rots every 5 or 10 years and they're always stripping windows off and putting new casings on them, or they're round doorways or walls, and every 5, 10, 15 years you see somebody fixing rot on a house over many decades, and they seem to like never fix the problem, because this is happening inside the walls, in the insulation of the faces of house and under roofs. All right guys, see you later.